The superheated steam tables display the properties of steam at various pressures in much the same way as the saturated steam tables. However, keep in mind, with superheated steam, there is no direct relationship between temperature and pressure. Therefore, at a particular pressure, it may be possible for superheated steam to exist at a wide range of temperatures. In general, saturated steam tables give gauge pressure, while superheated steam tables give absolute pressure. The following table is an extract from superheated steam tables. The various thermodynamic properties are taken at atmospheric pressure and for a wide range of temperatures, from 150 degrees Celsius to 500 degrees Celsius. Okay, now for the sake of demonstration, how much more heat does superheated steam with a temperature of 400 degrees Celsius and a pressure of 1 bar absolute have than saturated steam at the same pressure? From the bottom saturated steam table, the specific enthalpy at atmospheric pressure is 2676 kilojoule per kilogram. And from the top table for superheated steam, the specific enthalpy at 400 degrees Celsius and the same pressure is 3278 kilojoule per kilogram. So, the enthalpy in the superheat is as follows. Roughly 600 kilojoule per kilogram. This may sound a useful increase in energy, but in fact it will actually make life more difficult for you if you want to use superheated steam for heating purposes. So let's understand why. From the energy in the superheat shown on screen, the specific heat capacity can be determined by dividing this value by the temperature difference between saturation temperature, so 100 degrees Celsius, and the superheated steam temperature, 400 degrees Celsius. In this case, the specific heat capacity is as follows. So, 2 kilojoule per kilogram per degree Celsius. However, unlike the specific heat capacity of water, the specific heat capacity for superheated steam varies in a considerable way with pressure and temperature, and cannot be taken as a constant. The value that you can see now on screen, 2 kilojoule per kilogram per degree Celsius, is therefore only the mean specific heat capacity over the specified temperature range for atmospheric pressure. Keep in mind, there is no direct relationship between temperature, pressure, and the specific heat capacity of superheated steam. There is, however, a general trend towards an increase in specific heat capacity with increasing pressure at low degrees of superheat, but this is not always the case. 2 kilojoule per kilogram per degree Celsius at 125 degrees Celsius and atmospheric pressure is a typical value range for superheated steam. Now, the real question is, can superheated steam be used in process heat exchangers and other heating processes instead of saturated steam? Although not the ideal medium for transferring heat, superheated steam is sometimes used for process heating in many steam plants around the world, especially in the hydrocarbon processing industries. This is more likely to be because superheated steam is already available on-site for power generation, being the preferred energy source for turbines, rather than because it has any advantage over saturated steam for heating purposes. Now, to be clear on this point, in most cases, saturated steam should be used for heat transfer processes, even if it means de-superheating the steam to do so. Hydrocarbon processing industries often de-superheat steam to within about 10 degrees of superheat. This small degree of superheat is removed readily in the first part of the heating surface. Greater amounts of superheat are more difficult, and often it is not economic to deal with, and so are best avoided. There are quite a few reasons why superheated steam is not as suitable for process heating as saturated steam. First, superheated steam has to cool to saturation temperature before it can condense to release its latent heat or enthalpy of evaporation. The amount of heat given up by the superheated steam as it cools to saturation temperature is relatively small in comparison to its enthalpy of evaporation. If the steam has only a few degrees of superheat, this small amount of heat is quickly given up before it condenses. However, if the steam has a large degree of superheat, it may take a relatively long time to cool, and during this time, the steam is releasing very little energy. In addition, unlike saturated steam, the temperature of superheated steam is not uniform. Superheated steam has to cool to give up heat, while saturated steam changes phase. Recall, phase changes occur at a constant temperature. This means that temperature gradients for superheated steam can occur over the heat transfer surface. Additionally, in a heat exchanger, the use of superheated steam can lead to the formation of a dry wall boiling zone close to the tube sheet. This dry wall area can quickly become scaled or fouled, and the resulting high temperature of the tube wall may cause the tube to fail. So, to sum up, this clearly shows that in heat transfer applications, steam with a large degree of superheat is of little use, because it gives up little heat until it has cooled to saturation temperature. It creates temperature gradients over the heat transfer surface as it cools to saturation temperature, and also provides lower rates of heat transfer when the steam is superheated. This is the reason why superheated steam requires larger heat transfer areas. So, superheated steam is not as effective as saturated steam for heat transfer applications. This may seem strange at first, considering that the rate of heat transfer across a heating surface is directly proportional to the temperature difference across it. Now, one may say, if superheated steam has a higher temperature than saturated steam at the same pressure, then surely superheated steam should be able to impart more heat. This, however, is a false statement and will be looked at in more detail in the next video.